You may recall this slide from an earlier video. We have two forms of an exponential equation. In one of the forms, we have a base b, and this base can be represented as 1 plus or minus the growth rate. This growth rate is usually written as a percent change. We also have this form. The population, or whatever it is, equals some initial value times e to the rt. In these application problems, you're going to need to figure out which form is going to be the best to use. In theory, at least, either form should always work. These are both exponential equations. If we put in everything correctly, it should work out, but there are slight differences in the numbers, and sometimes one form is going to be a lot easier than the other. So the question is, how do you decide which version to use? And the answer is, looking at the differences between these forms, the primary difference is the growth factor, the rate of growth. And so you should use probably this a times b to the t if the change is either discrete or delineated. So if something is doubling or tripling or increasing or decreasing by a certain percentage. You should use this form of e to the rt when the growth factor is continuous. It's really useful for half-life problems, for doubling time problems, or any scientific applications. So let's sort through when to use what. When you see anything with the number e, I would lean towards the a times e to the rt. Whenever you have percent increase or decrease, as soon as I see that percentage, I'm going this direction, and I'm going to be using 1 plus or minus r for my b value. When I see half-life, you could do it either way. I like this formula better for half-life personally, but it's your choice. When you see bacteria divide into every x minutes, you're given that the base is 2. So in this one, I would definitely use a times b to the t, and b would be 2. If you're given a growth factor, I think usually that a times b to the t is easier. Let's look at this problem. Diseases tend to spread according to an exponential growth model. In the early day of AIDS, the growth factor, so the common ratio or growth multiplier, was around 2.2. So that means our base of our exponential is 2.2. I'm going to be using p of t equals a times b to the t power, and in this case, b is going to be 2.2. In 1983, about 2,000 people in the US died of AIDS. If the trend had continued unchecked, how many people would have died from AIDS in 2006? What we have right here is an initial value. 1983, about 2,000 people. So I'm going to say, let t equal 0 in 1983. I see later on in the problem, we're asked if this growth factor continued unchecked, how many people would have died from AIDS in 2006? 2006 is 17 years after 1983. That means in our problem, t is going to equal 17. We're also given an initial value. If 1983 is our time of 0, 2,000 people were already dying of AIDS. So our a value is going to equal 2,000. Putting this together, we have a formula, p of t equals 2,000 times 2.2 raised to the t power. Now I can simply substitute t in and evaluate. Population at 17 would be 2,000 times 2.2 to the 17th power. Just a quick side note for this problem, the numbers are slightly randomized. Maybe you can interpret this as being from different studies. They came up with different growth factors. We certainly didn't know what the growth factor was of COVID when COVID first started. Don't take the numbers as gospel, but the idea behind them is sound, and the range of the numbers is good. Evaluating this exponential expression, I got P of 17 equals 1,324,999,58. How accurate is this number? This particular question doesn't say anything about rounding, but just in general, with a growth factor of around 2.2, that means I should not assume that this goes all the way to the nearest person. I played around with this a little bit in my open math, and it looks like if we just use 4 significant figures, the program accepts the answer. I'm going to say this population would be about 1,325,000,000 people. Luckily, the disease did not continue spreading like that. Thank you.